All right. Welcome to Ask Mayfield Anything. I see people are joining in, so that's great. Glad to have you all joining us here this afternoon. And today we're going to be going over some discussions around 9540A. So a little bit of housekeeping before we jump into the topic at hand. And as you're getting going, getting settled in, this is very much, we liked the questions. We had a handful of questions, actually more than a handful of questions that came in prior to the webinar. And so we have those, try to address those as best we can. Some of them are integrated into the presentation, hopefully already. But for those of you that are out there, we'd love to get your questions, try and interact with you as much as possible. While you're doing that, if you would please use the Q&A section of the webinar, the Zoom feature there, just makes it a lot easier for us to manage the questions, make sure we see them, as opposed to using things in the chat. They get lost in the chat. So Q&A for those questions would be great. So thanks again for joining, and we can jump in because I know there's going to be plenty to talk about here today, so I don't want to delay too much. So my name is Ryan Mayfield, for those of you who maybe I haven't met before, and I'm the founder of Mayfield Renewables and been doing this webinar series. We're getting close to 4 years now. And one of the things I love about doing this is just being able to bring very smart people on, people within the industry. And we have that today. So being able to talk about topics that are pertinent for our industry, trying to help get answers. A lot of times it's questions that I have. And so being able to communicate with people has been great. Mayfield Renewables, we are a engineering consulting firm. And so we do a lot of engineering, traditional engineering on the electrical side of PV and solar plus storage projects. And we do consulting with both contractors and manufacturers. And then a big part of what I do, big part of what Mayfield's all about, is doing education. So doing these types of AMAs. We have our Code Corner series. We just launched with our partner Outfit doing a new series, Dispatches. And so trying to work with the industry, help disseminate information and make our expertise accessible for folks. Okay, our guests today, I'm going to let them introduce themselves as well, but I just want to thank them for coming on, bringing their expertise. First, we have Mike Nicholas from Hiller, so energy storage specialist and fire consultant. Mike was also previously with it was an Kern County, if I got that right, Mike, but as an AHJ. So Mike brings a lot of knowledge, a lot of history that he's had with energy storage systems and the codes and standards. So Mike, yeah, if you want to take a moment and introduce yourself to the audience.
Absolutely. Hi, everybody. Mike Nicholas, currently with Hiller Companies. Just retired from Kern County Fire Department, 26 years, captain there, and the assistant fire marshal who was over the battery energy storage division. Kern County quickly became the epicenter for a lot of the utility scale best projects that were coming into the state early. And as a result, we put together the first comprehensive submission guideline package that pulled from state codes and from all of the different associated national standards, and aggregated all those together with our consultant, gave it to the state fire marshal to use as a reference. Kern County currently has the largest battery energy storage project that's active at 3.2 gigawatt hours in the world. So glad to be with Hiller, and they were a big part of helping the clients through the permitting, installation, and witness testing, and ultimately testing and maintenance process. So glad to be part of the team, and thank you, Ryan, and everybody at Mayfield for having me.
It's great. I didn't realize that about the installation, kind of those guidelines and things like that, Mike. Is that, I'm just going to start asking the questions right now. Is that something that is available, or does Kern County make that, out there, put that out there for their own, getting their own permits, but also for others to look at and kind of understand learn the lessons that you guys maybe learned?
Oh,
Maybe kind of
absolutely.
the hard
Yeah,
way?
we made that a public document. We combed through all of the available permitting guidelines from other AHJs around the state and simply found an absence of that information. And due to the fortune of having our consultant, Bob Davidson, help us through that process, he aggregated all that, and it became our Bible for our submissions. And we're finding a lot of people across the state and across the country are utilizing that for their submissions.
That's really good to know. That's good information and kind of helpful for people out there to not reinvent that whole process.
For sure.
Great. Okay, and then we also have Josh Dinaburg from CSA, so fire test specialist for on energy storage. So CSA being a nationally recognized testing lab, and one of the and Josh, this is a question, I guess. I believe you all are one of, I think there's only like 4 or 5 that are doing 9540 testing for the listing itself of the batteries, but then you're also doing a lot on the fire testing, the 9540A stuff. So yeah, if you would introduce yourself a little bit to the client and I guess correct me if I'm wrong on that 9540 statement.
Yeah, thanks. Josh Dinaburg here. I'm a registered fire protection engineer. I've been doing laboratory testing in all kinds of fire protection related industries for the last 19 years. So that includes all kinds of pyrolysis and combustion, smoke and gas production, toxicity, detection of different fire signatures, suppression systems. And for the last 3 years now, very focused on these energy storage systems and their fire hazards. So I've been at CSA now for 3 years. They are a standards development organization, nationally recognized test laboratory. We do testing and certification for various products. So traditionally, that's always been a lot of electrical, plumbing, and gas work. So a lot of that electrical work has pushed them into the energy storage space. So I came on board as a fire test specialist to kind of advise as these fire and explosion hazards of the energy storage systems became more and more of a relevant topic, to help make sure that we're testing that in the right way, we're interpreting the results in the right way, and putting out some proper reports, as well as building a brand new laboratory to do that in the last couple of years as well. So as far as who's doing 9540A testing, I think in the US there probably are 4 to 5 total groups, and really only 2 or 3 that are doing them for certification purposes as it relates to, a 9540 certification.
Yeah, I saw that list recently or heard somebody talk about that, and I was surprised at how few there actually were. So yeah.
Yeah, I think there are a few other test laboratories, but to use it for any certification, you'd probably have to get one of those 3 testing certification bodies in as well.
Yep. Makes sense. All right. Well, thanks for that, Josh, and thanks for joining.
Yeah,
appreciate your perspective, and I know we have a lot of good stuff to talk about. So let's jump into the topic. And so today, 9540A. So we're talking about we're really focusing in on the testing procedure. So the procedures for understanding what happens when the cells, the modules, the units go into thermal runaway. What does that mean? And so maybe even starting with some of that basic language is going to be something that we are looking or we'll be talking about as we're going along here. So let's, click that button. So first off, to kind of just jump start us here is 9540A testing itself. And love to get, Josh, I know you're intimately involved with this. Mike, I definitely want to, get your input here as well. But you see here for the folks that have seen or are on the call, this is the general flow for what the 9540A testing is going to look like. It's going to start at the smallest level, the cell level test, and it will progress down through the module level test. And as we were going through I've heard kind of differing opinions on this. So I'll probably use language like pass fail. I know Josh in our calls has talked about, providing the necessary information to, and it was much more eloquently put than that, but their data is what we're getting at here, right? So we are gathering data, we're gathering information on what happens when the cells go into these specific or have specific situations happen. So we start off at a cell level test and testing for if there is thermal runaway and what gases are released. So those are really the 2 main things that are happening here. And just starting off here at this most basic level, the individual cell, Josh and Mike, you correct me if I'm wrong, but from what I've seen, from what I've heard, is there haven't been any cells, lithium ion, we should maybe be very specific, lithium ion cells that have been able to go through a cell level test and not go into thermal runaway. Is that a correct statement to say?
Yeah, I could comment on that quickly. So predominantly what you're going to see out in the industry right now are lithium ion batteries, for their energy density, capacity, lifetime. That lithium ion chemistry is almost certainly going to produce flammable vent gas. The way those cells are constructed, when they get hot, the electrolyte inside is going to produce hydrogen, carbon monoxide, and a lot of hydrocarbons. I have never seen a lithium ion chemistry that would not produce flammable gases as you exceed high temperatures within it. As far as thermal runaway goes, you could practically produce this in any electrical carrying cell as long as you create an internal short. So you're converting that electrical energy into thermal energy through the short in the cell itself, and you're getting an increase in temperature that you're not causing or controlling. So most cell chemistries will go into what you would consider a thermal runaway. I've seen that as low as 20 or 30 degrees as it just kind of spits out its electrical energy. That's generally not considered a hazardous thermal runaway, but by definition is a thermal runaway. It's really that non-flammable vent gas that differentiates lithium cells from various other chemistries. Lithium ion cells are going to produce flammable vent gas and then inherently not achieve the fire performance goals of the cell level test.
So it's interesting to me. So, and we have some more language towards the end of the presentation about this, but so cell level test, if the cell does produce flammable vent gas, then the second test, as we see there, talks about containment of the thermal runaway, but then non-flammable gas, vent gas from the cell level test. So I guess my question there then becomes, if a manufacturer goes through and does a cell level test, they get flammable gases, do they just leapfrog use the module level test to provide the information or to produce the proper information? Again, I'm trying to say not pass for the module level test. If there's flammable gases present, then it's not going to be able to, it would not pass that test.
No, so if you're measuring flammable gases from the vent on the cell level, there's fundamentally no way to end this test process at the module level. A unit level becomes practically required. The main reason for the module level testing is proceeding straight to a unit level without knowing what will happen is pretty risky and financially dangerous, right? So the module is almost a verification test of does our abuse method result in some propagation? Does it result in full propagation? Do we get fire when we test this module? How much flammable gas do we produce from the module as a whole? And then use that knowledge to go forward to a much more extensive unit level test.
Got it.
But if you have a lithium ion chemistry, either you're misunderstanding the standard or someone has been misled to stop at a module level. That's
okay.
Practically impossible.
Interesting. Okay. And as my understanding too, so we are, again, we're focused on 9540A today. I'm going to quickly divert over to 9540 just for a comment or a question, or I guess a comment. So we're about to see the third revision being implemented. So September of this year is when the third edition is going to be. And my understanding is specific to residential unit level testing is going to be explicitly called out there. So I think like what you're saying there, that doing the module level test to get that information, understand what happens before you go into the whole unit level is probably an important aspect and something that the manufacturer should be supplying with that test data.
I think it bears mentioning.
There's some. Oh, go ahead, Mike.
Sorry, Josh. I think it bears mentioning at this point too that when we're looking at it from a real life application, there isn't the assumption that suddenly every module and every cell will simultaneously go up within the unit, right? So from an emergency response perspective, this is a scalable test that's yielding data that's going to inform ultimately the hazard mitigation analysis and some of the thermal runaway prevention that's going to be integrated into that submission. So these are really integral tests to take at each level and to really try and aggregate that information. And when you start getting into the module level test also, you're looking at additional combustibles that weren't present at the cell level.
Yeah, I would add to that there's a lot of really good data that comes out of both the cell and module level. There's the total amount of gas volume produced and the constituents of that gas, how flammable and explosive it is. And then there's also the rate of gas production from an uncontrolled thermal runaway. And then combining that single cell into multiple cells going into a staggered progressive thermal runaway gives you a really good idea of how much gas is produced and how quickly. Which now you're mentioning the third edition 9540, which will also require some explosion prevention protection systems. And that knowledge becomes really fundamental to designing those systems to work effectively.
Great. And there's a couple comments here wanted to address. I think it's great. So David's talking about the use of the language around lithium ion, and Angel's asking a question about different technologies. So we have, under the lithium umbrella, if you will, we have a lot of different cell types, a lot of different technologies. And so that's a very good point, David, that we do have these different technologies, these different chemistries. The flip side of that is when we start talking about different code standards, 855 comes to my mind explicitly that there is no differentiation between different technologies. And so I think the question that is being also asked here is, Josh, is there a differentiation in the 9540A testing? Do you approach an NMC versus an LFP any differently, or is there, what fundamentally are there differences in that testing?
So I do from my hazard analysis standpoint. If I'm going to be protecting my lab, where I'm going to put instrumentation or exposed wires. The major difference, and the reason I would kind of push back against David's comment there, is LFP and NMC cells go into thermal runaway. They produce flammable gases that have the potential to ignite. They create a really high temperature on the surface of the cell that can, spread heat through conduction to the cells next to them. Once you get things lit and ignited, there's almost no difference between the two other than the rate of propagation. LFP cells will go into thermal runaway at a little lower temperature and have a little lower peak temperature. So they are less likely to ignite and self-ignite. So you're a little more likely to get gas production without a sustained fire compared to an NMC. But they can both burn very readily. They both produce pretty similar gas concentrations of hydrogen, methane, propane, heavy hydrocarbons as well. To make any statement that any of them are safe at the cell or module level is not correct. I don't test them any differently. I get very similar results at the cell level. At the module level, I may get different levels of propagation or different likelihood of fire. But other than that, it's still the same conclusion at that module level, and a unit test is still required.
Yeah, that's very helpful. And just because, yeah, having seen the different, the different temperatures at which the different technologies do maybe go, the thermal runaway, those temperatures, what maybe, and how they act does look a little different. But I think the point of the testing is, we've got to get there one way or the other. And then once we get there, kind of how does it go?
Yeah, I've seen both result in infernos that are fully burned, fully consuming, getting all the cells, creating explosion hazards and heat flux hazards to adjacent surfaces. So
Sure.
There's nothing in the standard that makes you treat either of them differently. And from a testing standpoint, similar results. You know, you may just be less likely to have the fire that at the unit level will not create wall temperature rises, adjacent systems, adjacent cells exceeding vent temperatures or dangerous heat fluxes from an LFP that does not self-ignite.
Sure. Okay, that's great. Very helpful. So kind of going through, cell module unit level. So the unit level being, an individual unit. I guess one of the questions I would like to address or look at here is this installation level. So in my mind, this is, much larger scale. Mike, this might be kind of some of that experience you had with Kern. I'm curious if, you were looking at installation level tests, how that was conducted. Where do those come into play? Like at what point would I be looking at a installation level versus a unit level test?
I think from an AHJ perspective, one of the things that we were focusing on is the large scale burn test. And I don't know if the utilization of installation level being synonymous with a large scale burn test is a misconception. And I don't want people to get those misconstrued. But when we're looking at a large scale burn test, that's going to yield more of the information from the first responder perspective. That's going to give us information to make tactical and strategic decisions about engagement, because we're starting to see these modularized strings of enclosures that have wire chases and connections between them, smaller footprints compared to our large C-train size, 40 to 50 foot C-trains with full of batteries. So when we're looking at these large scale burn tests, we need to know definitively if we're going to be facing 1, 2, 3, 20 of these individual enclosures that are going to be basically on fire, or are we looking at a single enclosure that doesn't propagate to an adjacent enclosure? And I think that's the big emphasis from the first responder perspective, is propagation, which is ultimately what we're looking for in that large scale burn test. And again, not so much a pass fail, but more of a data gathering and information based utilization of that data.
So I would add to that just a little bit. The reason I don't like pass fail here is that we're trying to achieve fire protection goals, right? If you look at the what you're testing for at the unit level, you're looking for adjacent system temperatures and at the spacing that you're testing these different units set from each other. You're looking at adjacent walls and structures not exceeding the temperature at which they may ignite. You're looking for safe heat flux. If you don't achieve that at the unit level, it generally means you had a large scale fire, right? That you had an ignition, this unit lit on fire, flames were coming out the top and the sides. It was putting an excessive amount of heat flux on adjacent surfaces. So that's units and walls near it. So the installation level then becomes necessary to come up with another way of achieving those fire protection goals. So the typical installation level is, put sprinklers up on the ceiling, spray water down on the adjacent surfaces. Your wall's no longer going to exceed 97 C above ambient and can ignite, but you're still going to have that same fire. Or maybe something in the installation level detects it early and extinguishes the fire before it happens. And now you no longer have those threats to the adjacent units or adjacent walls. So if you see an installation level test, you may want to look back at the unit level to learn what happened without those fire protection systems to mitigate those hazards.
Interesting. Okay, that's helpful. And yeah, I personally haven't seen a lot of the installation level, usually unit level. And so, but I think that's good advice, Josh, there, of going back and looking at those results, getting that information from the manufacturer on what the unit level testing was providing, and providing and what that data is telling us. All right. I know any one of these we probably could spend a lot of time on, so I'm going to try and keep us moving forward here. But this, I think, gets into maybe the most recent question here that came across. And so the question of, is 9540A a large scale fire test? And continue talking about this in the next slide when we start talking about AHJs and what they're, what they're looking for, what that data is trying to tell us. But this slide is, something that folks on the call maybe aren't super familiar with looking at this. So I guess I'm going to ask Josh to jump in and kind of walk us through this. But one of the things I do kind of want to, if you could throw in here, Josh, is, so we're looking at some cells going into thermal runaway. What does that look like in the lab? Are you heating it up? Are you driving a nail through it? Are you running it over with something, crushing it? What does that physically look like in the testing process?
Sure. So I guess there's a slight disconnect between what the fire service and the building codes were asking 9540A to accomplish and what the consensus standard eventually became. And that disconnect was, the fire service wanted to know, how do I attack this? A lot of what Mike was talking about. How do I attack this? How far could this spread? What's kind of the maximum credible event I could see? And sort of what 9540A took is attack of, okay, we have a thermal runaway that occurs, some internal cell failure, some fault in the system. And how far does it propagate? And is the system designed to stop it from kind of propagating and getting worse? Through insulation or cell spacing or module spacing or air cooling, whatever it is. So the goal of 9540A is to get a cell into thermal runaway and see what happens. So the most common way to do that is just a thin film heater on the cell, a tape with resistive wire running through it, wrap it around, and kind of ramp this thing up slowly to see what happens. It's not really realistic of any actual real world failure. An internal short's not going to look like that. A puncture from a nail or a bullet or a forklift isn't going to look like that. But it helps us learn. It helps us control the thermal runaway by seeing the temperatures at which things happen by doing it slowly. So heat this thing up from the outside. At some point, it's going to vent off some gas. And then if you keep going, at some point, it's going to get hot enough that, it shorts itself internally and all the electrical energy becomes heat very, very rapidly. So the way that 9540A has been played is at that module level, you need propagation. So I can't just put one cell into runaway and it's, a meter from every other cell and nothing happens. I have to get something to propagate. So the manufacturers have sort of, I don't want to say gamed this, but met the language of the standard to get one cell to propagate to another cell, and then the whole event stops with no ignition, no fire, just one cell worth of gas. The next cell touching it on the side gets hot enough, it goes into its own reaction, vents its gas, and then nothing else happens. So that is now the goal of a manufacturer at the 9540A level, is to limit all the damage to that level. And that is really indicative of a good design. If it's not propagating beyond a single cell failure, that's great. It means most real world failures of the system or defective cells or anything else isn't going to progress to that full scale hazard in most scenarios. So what you're looking at in the graph here is just a slow ramp of that yellow temperature, that initiating cell. You get it to go into a thermal runaway, it spikes up there at that first purple arrow. And then that is enough heat without it not igniting on fire, right? It's just the electrical energy turning to heat. There's enough heat there to get the cell touching it on the side to go into its own thermal runaway event. And then that's all that happens. So in an ideal manufacturer's world, that is the goal of NFPA or UL9540A.
So you being the manufacturer have propagated, you've initiated the thermal runaway in cell number 1. It propagates over into cell number 2. I guess I'm like, why isn't cell number 2 doing the same thing into cell number 3? If they're the same distance, if they're able to be, if they're touching, I can't imagine. I guess I don't know the internal.
So yeah, so this is where the intent of the test actually results in some questionable designs, because the test requires propagation. So if it doesn't propagate, I may have to heat, 4 cells in a diamond and hope the one in the middle will go. But the more and more cells you start heating, the more likely I create a catastrophe. So I'm actually being punished for my good module design, right? Which is, hey, propagation's really hard, but now my test looks like a catastrophe because I had to heat
Because
4
you have to
cells.
do that. Got it.
So
which you're going to have a higher likelihood of propagating into more cells.
yeah, so what I'm seeing
Hmm.
more now is actually, rather than heating more cells, I think that this has been accepted into the next edition, is actually maybe remove some insulation or material between two. So you get the second one to go just like in the chart here, but then it doesn't spread anywhere else.
Okay.
And it's a realistic failure. It demonstrates something that happens in the real world, but it does not create a large scale fire test unless something has gone awry.
Okay. I'm gonna put a pin in that large scale fire test comment for a second because I want to. Well, actually, this is related to it. So I guess ultimately is what is a true large scale fire test. But before we get there, the 9540A good question came in saying, doesn't 9540A require an internal fire condition? So is 9540A requiring that something lights on fire in order to gather that data completely per the testing standard?
I lost my mute. No, in fact, if you light the gases on fire, you're gonna now be producing a lot more total heat, and it becomes a lot more likely you're propagating and propagating. It becomes an uncontrollable event. So there is discussion about putting ignition sources in there to make sure the gas is light on fire as one means of turning this into a larger scale fire event. But right now, if that cell isn't creating sparks, isn't, the surface isn't above the auto ignition temperature, or the adjacent electrical, capacity of cells aren't creating some ignition arc, it does not ignite and it does not have to.
And therein lies, Mike, go ahead. I see you had something to say there.
Yeah, I think that's actually a fairly relevant point because in our trainings to first responders on these large scale or utility scale projects, we always tell them that there are two safe states of a battery, normally operational or fully on fire, because everything in between poses a risk for explosion. When you have unburned fuel that's accumulating in a closed container, you have all the makings of a pipe bomb on a large scale. And so for us, you don't want that deflagration to detonation transformation because you get some large pocket of unburned gas that finally reaches an ignition point, and now you have this whole thing going. So you've seen some of these battery manufacturers that have come up with engineered solutions to this NFPA 69 deflagration and detonation protection or explosion protection, where they're actively lighting off any gas that is released and basically sacrificing the enclosure and burning all the batteries up. So once it's on fire, at least we know it's not going to blow up, which sounds like a strange win, but that really, from a first responder perspective, we need to know what that safe level of engagement is in distance to be able to even put an incident command post. So that's some of the reason for the big emphasis on the large scale burn test, because the cell module and the unit level are going to give some information, but really truly the more real life scenario is going to be a large scale fire test in a fully populated enclosure with enclosures placed adjacently like you would see at the actual job site, again populated with batteries, so that you know whether that fire in that device under test will actually negatively impact the adjacent enclosures and batteries, causing another cascading thermal runaway in there. And so that's what's being worked on right now. And this most recent code revision is also some language and definitions around what is a large scale fire test, how to standardize actually igniting them. Like Josh was saying, are we removing installation? Are we putting in some torch device, or, how are ceramic heaters? So this is some of the confusion from the testing side of it, that the testing labs are also providing some good insight and information and trying to assist in standardizing this approach.
Yeah, and so I would love to spend a little more time with both of you on that, because I see questions coming in, and I think this is almost the heart of the matter of a true, and we have it there on that third bullet, a true large scale fire test. So what is that? And it's seemingly, and actually maybe I'm just going to go to the next slide because it has some information, some stuff here about that. So 9540A is not requiring that we actually light something on fire. There is language in there about doing a large scale fire test, but thermal runaway testing, and so you can see in this letter here that we have from the San Jose Fire Department, where their big takeaway is thermal runaway testing is not equivalent to large scale fire testing. So the question I'd like to pose to the two of you is, well, what is large scale fire testing, and where does that fall into the world of 9540A? Is 9540A giving us, is there a way for a manufacturer to complete 9540A and also do a large scale fire testing and get that data to us?
Yeah, actually, it's really convenient, and a good way to use up the material needed from the unit level test. If I have a couple of burned up modules, it's nice to replace them with new modules and burn up the extent of the unit and sort of do it after unit level testing. Stick a flame in there, stick some igniters, increase the abuse, and drive that unit into a full fire. That actually helps consume a lot of that stranded energy that's dangerous for the labs to get rid of as well. And it's a good way to sort of, use the same material at the same time at the same lab and get all those tests done.
Yeah, and I've been to a couple different test labs, and I don't know that it's a complaint per se, but from the manufacturer's perspective, they're doubling down on the inventory that's going to be destroyed through these 9540A tests and then a second large scale burn test. And as it stands right now, unless you have a way to salvage, like Josh was mentioning, some of the used material at the lower cell module unit test, that large scale burn test is really designed to become an all encompassing fire within that enclosure and within those batteries. Now, Josh, is there a minimum state of charge? Is it assumed to be 100% state of charge for this large scale burn test?
So nobody's dictating that, but I've had some manufacturers request to go at some lower states of charge. And I've warned them that, you're allowed to do that. No one's telling you to go at 100%. But if I'm your approval agency and you say, hey, it doesn't burn or it doesn't spread at 80%, I go, well, good for you. I'm still not approving that. Show me 100. So I don't see any reason not to test at 100 and see what happens. I think that your acceptance out in the AHJ world may be limited if you don't.
I think that brings up a good point, which goes back to Josh's emphasis on, and mine as well, on not utilizing, the nomenclature of pass and fail, because I think it creates the optics from the manufacturers that, hey, if we do this and it has this level of involvement of the fire, or we use too high a state of charge, or that is going to create some sort of negative perception about the technology. From the AHJ side, it's like, I want this thing to burn hot. I want it to burn completely. I want it to be a raging inferno. I want to know worst case scenario, because we're the ones showing up in the middle of the night with, some overtime crew that's never seen the, installation site, and trying to figure out what we commit as far as resources to protect exposures. We risk a lot to save a lot. If a life's involved, we're going to be doing a lot more than we are if it's just property that we're looking at saving. So I think if we abandon some of that idea that there is a pass and fail criteria with these, and use it more as an educational and informative data collection test that will then go into the hazard mitigation analysis that's site specific to that technology, that becomes a little less fearful approach for manufacturers to engage testing labs, in my opinion.
Yeah, I would comment on that as well. So there's so many things that could be learned from that fire test. And it is an expensive test that consumes a lot of material and, can only be done in a few places. So there's no reason not to address as many of the fire services concerns, the insurance agencies concerns, and the community risk reduction concerns. You know, toxicity, plume spread, smoke deposition, water, water usage, and all of that. So I don't see any facility or installation that's just a cookie cutter, pass fail. Good job, you passed the large fire test. I think that they really need to be looked at with a lens and understand what it means for those installations and those situations. It's more about data than it is, yup, you check the box. I did want to address one comment I'm seeing in the chat about 912 in 9540A for the internal fire condition. So I agree. This is some bad language actually that's in there at the unit level. It's calling for an internal fire condition in accordance with the module test, and then the module test never calls out this language and only says produce a thermal runaway and a propagation. The general interpretation here is that an internal fire condition is that thermal runaway in a cell. You will get CO2 production. There is combustion happening. So even if you don't have a sustained ignition of a flame, a thermal runaway is inherently an internal fire condition of the cell. You are creating pyrolysis gases. There is a combustion reaction occurring, whether you light it on fire or not. So it is a bad use of the language there within the standard, but no one is interpreting that statement at the unit level that you need to ignite those gases or have open flame.
Oh, interesting. So there is that language in there, but the way that that's being interpreted is by the technical definition that the runaway is meeting that definition.
Yeah, and I think we could have debate about this all day. But at the module level, it says in accordance with the module level, which does not call out that statement and does not require you to have a flame or flaming condition. So it's vague and it's not great language. And I think it could be interpreted in multiple ways. But the general interpretation, I think, among the testing certification industry is that thermal runaway is an internal fire condition and it does not require open flame.
Okay. Well, let's move on to the next one because I actually have some questions and it's related to some stuff that we have on here on this slide itself. So in relation to all that, Josh, I'd love to have you talk to us a little bit about this consensus standard. So if we are saying 9540A is providing this certain level of test, but it's not actually a large scale fire test, the question then becomes, well, what is a large scale fire test? And from my understanding from our conversations, there is a consensus standard being built around that. And so I guess, could you talk us through what that looks like, where that's at, who is doing that, all that kind of stuff?
Sure. So UL has gone and put out 9540B, which we noted there at the bottom for residential ESS. That is attempting to address an ignition source and having a fire test for those residential ESS systems. So the main difference there is there's actually an igniter system where the gas comes out of the unit itself to try to light that venting gas on fire and get flames outside the ESS or inside if there's enough oxygen flowing there as well, and create this extra heat and the extra, heat flux on adjacent surfaces and units. So that was an attempt to do that for the residential. I know 9540A is looking into including some additional ignition sources to drive that to more of a fire test as well. At CSA, we're also working on, it's called CSA C800. It's a reliability test for ESS. So the thought process there is that assesses a lot of external stimuli on the ESS. So, a single cell failure is generally not going to create this event. That's sort of what 9540A is testing now. It may take an external event to drive one of these large fire events, a flood, a wildfire exposure, a a lightning strike, some giant grid problem, or overcharge of an entire module. So that is being worked on as well, where we're trying to put together, how do you test this? How do you ignite it? What's the right abuse method? Do we open vents and louvers to drive enough oxygen in? Do we keep those closed? If there's deflagration panels, do we keep those open? How do we measure the heat fluxes at other places? What are we concerned with? That's either of those, and none of that is going to be standardized or have a defined method for the next year, maybe year and a half. I know myself at CSA, I'm trying to put out this summer how I recommend you do this, with a lot of that criteria, but ultimately, until there's a consensus, it's manufacturer driven. The manufacturer needs to understand their client, the AHJ in their jurisdiction, the community they're trying to put this in, and make sure they address the specific concerns on a, I don't want to say a site by site basis, but on a system by system basis, and make sure that that large expensive fire test is going to give them, you know, an indefensible report to go to many jurisdictions and prove what they can or can't do. But really right now it's very manufacturer driven.
Okay. And Mike, kind of along those terms, I'm curious to hear from you. I'm making a presumption here that you know, having conversations with others, having, you know, been in the position you were at with Kern County, just guidance that you're giving people, you know, there's the difference. We saw that letter from San Jose Fire Department where they're kind of drawing this line in the sand of the what they're considering large scale, or they're not, I guess, not considering large scale fire tests. So I guess my question to you is, you know, just kind of, how are you looking at that? How are you talking with folks? You know, what should they be asking for from that AHJ perspective?
So I think, to Josh's point, right now we're in a position where the AHJs are ultimately going to be determining whether or not the extent of the test was sufficient, right? And then how that informs a submission package as far as some of the failure modes and effects that can happen as a result of these technologies that are site specific and technology specific. So when we're looking at these large scale burn tests, and a developer or manufacturer goes to a testing lab and says, I want to test, and here's how I want it tested, then we're running into a situation where if the developer isn't completely aware of what that large scale fire test is intended to prove or not prove or demonstrate, we've been, you know, in positions where we've had to say that these developers have to go back and get more tests done. And now you're talking about a delay in getting access to the lab, setting up these tests, which are very costly, like Josh mentioned. And so from an AHJ perspective, I think the more uniformly we can address this issue and really be able to say that we want a large conflagration, we want this thing on fire in order to really know what we're going to be facing. And I saw a comment in the chat about McMicken, and McMicken really was kind of the origin story here in the States for what these technologies can pose as far as a threat. And I think the comment was about, you know, the safe state being normally operational or fully on fire. So McMicken had a basically unvented and unmonitored enclosure, off-gassing, displacing oxygen, waiting for this, you know, unfortunate scenario of the door being breached and the firefighters assuming it was an electrical utility instead of a battery energy storage. And so the industry now is focusing a lot on how we use this information that we get from these different 9540A cell module unit level and large scale burn tests to inform what an effective ventilation rate is to have to prevent that lower explosive limit from being maintained below the 25% LEL. And so, you know, when our gas detectors are set up to trigger at 10% lower explosive limit of hydrogen, say, then we're not going to get to that 25%, which poses, you know, a much more significant life risk. And that early detection and integrated and coordinated ventilation becomes our primary means of explosion prevention. which is exactly what happened to McMicken. So once that fire has ignited the gases that are present and it's overcome, say, the exhaust or the combustible gas concentration reduction system, now we have open flame venting that's to the outside. And now that's the safe scenario I was talking about, not this smoldering, off-gassing box filled with, combustible gas waiting to get a lean enough concentration to make it ignitable. And so these are some of the takeaways that we learned from McMicken. And then we have Chandler and Moss Landing and others. And in fact, there was one in South Korea here the other day in a battery manufacturing plant that killed, I think, 22 or 23 people. And that wasn't even in BESS enclosures. These were, you could see the individual cells rocketing and exploding within the plant. There's some videos out there. So I think it's important from the AHJ perspective and to inform the industry why we're asking for these things, how that impacts design, installation, witness testing, and ultimately first responders' comfort in having these in their backyard for a 20-25-year term, long-term relationship. So that's how we're looking at these large-scale burn tests as being really informative and definitely influential in how the NFPA 69 mitigation comes out of these tests for us to be able to have these hopefully non-explosive designed boxes in our backyard.
Yeah, and I think that's all great information, and kind of pointing to those specific examples. I think one of the things that as an industry we're looking at, and we're starting to hear about, hopefully not a whole lot, but there have been some large scale fires. There was the event you were talking about in Arizona. There were 3 separate incidents in New York last summer. There was an event just happened down in the San Diego area just recently, and so something in California prior to that. And so one of the things I think that we need to be thinking about and considering is, as far as I know, in each of those cases, the event that ultimately caused the failure, it wasn't a cell failure. It wasn't something that was wrong with the units themselves, but it was an external event. It was some sort of liquid got onto the batteries and created a short. And so lightning strikes, things like that we've look at and see. But there might be that ignition source. I guess is kind of the point I'm trying to get at, is the cells are in that runaway, they are venting gas. If there is an external ignition source, we need to understand what that is. And I think that's one of the big drivers of what a true large scale fire test would be trying to accomplish. So going to kind of get close to wrapping up here. We're getting close to the top of the hour, and lots of great questions that have come in. And we have this list of kind of just takeaways, considerations. I thought a really good question came in, or it's almost even a challenge, I guess, to both Mike and Josh. Giving the elevator statement or the elevator pitch on what it means to have 9540A. So if I am a manufacturer or I'm a EPC taking this to my AHJ, what should I be pointing out? What is that elevator pitch on the UL9540A test report and the data that I'm having included with it?
I guess I could comment on that. So what 9540A proves is that for many typical internal cell failures and faults, the system has been designed to prevent catastrophic fire damage. So whether that is by limiting cell-to-cell propagation, so that one cell failure does not result in the cascading failures, or that is by separating modules from each other, where a whole module either on fire or entering consumable thermal runaway doesn't spread to the other modules, or by protecting adjacent combustibles from the unit itself on fire, through a sprinkler system or other fire safety systems. That the combination final design of the system limits the potential damage from typical cell failures. And that's about where I'd leave that.
Okay. Mike, do you have an elevator pitch on 9540A?
As far as where it's going, or
Just kind of just the what is it? Yeah, it is if I'm wanting to present this data, like, what is the, I guess, the point to the AHJ, or what would I be wanting to bring attention to the AHJ? There's a lot of AHJs out there that don't have the ability. In Kern, you guys had this huge installation, and so of course had to take time, resources to look into it, but maybe not every AHJ has that. But as an installer bringing this to the AHJ, what would be the highlights? What is it, the stuff that you would want to be bringing to their attention of what this actually is providing for us?
so again, the 9540A is an attempt to determine at various levels what the associated risk with that technology is, right? And the large scale burn test is an externally forced, artificially created fire within this unit. So I think there was a comment in here saying, we don't want it to burn hot. We should be rewarded as manufacturers. And to the point that the technology doesn't by itself go into these thermal runaways of these large scale burn tests is a success. And we are appreciative of that. And that's showing, incremental improvement in that technology. So when we're looking at having to externally force these enclosures into a large scale burn test, that was the comment that, we don't want it to just be a partial consumption of this enclosure and call it quits and try and put the test out. It's like, we want to see the full thing go. We want it to be completely on fire because, again, from an AHJ perspective, we're looking at worst case scenarios because it's always going to be that bad day, that unusual set of circumstances. And when we're even looking at these failure modes and effects analysis, we were scolded a bit at the AHJ level for saying, hey, you need to consider certain criteria that you haven't. There could be some act of nature that causes a failure. And one of our sites got struck by lightning. And suddenly that became yet another failure point that we had to incorporate into that FMEA. So when we're looking at this is an emerging and growing technology and industry, right, that we're looking at. And I think from the manufacturer's perspective, they keep trying to create safer and safer technologies and then adding in a lot of these thermal runaway management systems, direct inject NOVAC, direct inject water, StatX. And from the AHJ perspective, one of the most vetted and time tested is going to be early detection and coordinated exhaust, sufficient to be able to prevent that level of combustible gas from reaching the 25% lower explosive limit. And so a lot of these tests are designed to give us the parameters and the data to be able to help design these thermal runaway management systems and these combustible gas concentration reduction systems to keep them at that lower level. So these tests are still evolving, and make no mistake that in the next iteration of 855, you're going to see a much better effort at trying to define and create standardization in these tests, in these ignition parameters. So, I think this is a good example of the industry working with regulating agencies, working with general contractors, and trying to come up with an idea. Well, this is what I'm concerned with from my vantage point and my lane. And this is what we're trying to do on the manufacturing side. This is what we're trying to do on the installation side. So this is still very much a cooperative effort. And we do appreciate the fact that there are new and innovative ways of coming up with managing these risks associated with these technologies. But understand that each new iteration of a technology also requires a certain amount of time to be operational before we're aware of some of the associated risks.
Yeah,
So
yeah.
instead of being accused of moving the goalpost, we need to realize that every incident of reference informs us as to the next direction to try and grow.
Right. As the industry evolves, we're having to evolve the standards and stuff as well. Well, we're getting right up on time, so I do want to make sure people see our contact info. Lots of great questions. A couple things I do want to point out. This one should be a real quick and easy one. 9540A has a new revision. Is that next year that we should be seeing that? And Josh or Mike, do you know? Is that kind of the timeline on that? I've heard something mid-summer next year.
Yeah, they're integrating public comments right now. It's going to be
Okay.
still going through this process, but yeah, it should be here shortly.
Okay. Okay. Yeah, and to like a lot of points that people made, Jason, you made a great point. New tests need to be evolved. Josh and CSA are involved in this consensus standard, so definitely work to be done to make sure that our industry is doing everything and being as safe as possible. One last thing too, I do want to just point out there were some questions, some talk about the IRC, some stuff about marked for residential dwellings. We actually, Steve Neal sent a great resource ahead of time. So in our follow-up to everybody, I'll make sure that we include that link because there was an article from UL that discussed that. So I think that would be useful since I saw that come up a handful of times. All right, so gonna wrap this up. This is, very much what we love to do. We do a lot of education at Mayfield, so I encourage you to take a look at our website. We have courses on topics, around ESS, codes and standards, things like that. So very much appreciate people taking a look at that and giving us feedback on that. And then finally, next month, we are going to have our friend Jason Fisher, come on. We're going to talk about UL3141, power control systems, energy management systems, where that lands in code. And so very interesting discussion, a lot of things moving on that. So look forward to that discussion at the end of July. So with that, Mike and Josh, I really appreciate your time. We've gone just a hair over, but lots of stuff, lots of great questions. And thank you for everybody that participated out there.
Thank you for having us. Appreciate it.
Yeah, thanks so much. Really happy to be here.
Great. Thanks, everybody. Have a great day.